Hi, I'm Adam, and this is part 1 of a 2-part mini-series. Part 1 covers the design of this retro-inspired mechanical keyboard, while part 2 will cover the build, firmware, and of course, using it. Let's get started. And now a quick message about PCBWay.com, my favourite PCB manufacturer, who help make these videos possible by sponsoring them. Get your project going with PCBs starting from just $5 for 10 boards. And with the new multicolour silkscreen, your boards will look like artwork. PCB prototype the easy way with PCBWay.com. Ever since designing and building this macro keypad, I've wanted to give designing and building a proper mechanical keyboard a go. Now, if we take a quick look at the schematic of my macro keyboard, you can see that each of these switches is connected to its own dedicated GPIO pin on the microcontroller. The issue with this is that it doesn't scale. If I wanted a keyboard with 88 keys, then I'd need a microcontroller with 88 GPIO pins. Fortunately, there is a more efficient way of connecting the switches using something that is referred to as a keyboard matrix. This example matrix consists of 4 columns and 4 rows. The columns are numbered starting at the left with 0, and the rows are numbered starting at the top with 0. Each row and each column are not electrically connected, so when you see them cross like this, there is no connection there. That's the job of the switches. When a switch is pressed, it shorts a column to a row. Let's take a look at how this works. So if this switch here gets pressed, so it is on, then column 0 gets shorted to row 0, and the microcontroller will see this. And if this switch were to be pressed, then column 1 gets shorted to row 3, and again, the microcontroller will see this. So you can see that this small example of just 8 connections, that's 4 columns and 4 rows, allows up to 16 switches to be connected to the microcontroller, and each switch has a unique row-column address, making this method of connection much more efficient in terms of required GPIO pins on the microcontroller. In reality, these matrix designs also include 1 diode per switch, and this is used to allow for multiple key presses at the same time. Think about when you need to perform keyboard shortcuts. These are often 2 or 3 key combinations. Now that I know that I'll be using a keyboard matrix, I need to work out how many keys I want on my keyboard. I can then design my matrix and thus go about selecting an appropriate microcontroller that has enough GPIO pins. To design the layout of the keyboard, I used and recommend keyboard-layout-editor.com. You can either build your own layout or start with one of the presets. I want a UK layout, so I'm going to start with this ISO 105 key layout. You'll see that with the ISO layout, you get a large enter key, the British pound symbol on the 3 key, along with a few other small differences compared to the ANSI layout. I don't want a numpad on my keyboard, and removing these keys is as simple as selecting them and pressing the delete key. And you can even select multiple keys at once. This is the keyboard layout that I want, so I'll need to draw a matrix, count the number of rows and columns, and then select the appropriate microcontroller. A tip here is that you can save this design to your GitHub account. Just click Sign in with GitHub at the top right. I really recommend this as you'll be referring back to this throughout the keyboard design. Next, I took a screenshot of the keyboard, and still within the Windows Snip tool, I drew out how I wanted my columns to be connected. In theory, it doesn't matter which keys are on which column. Then I added the rows, and for ease of visuals, I did this in a contrasting color. Finally, I added some text in Photoshop. So now you can see I have a total of 17 columns and 6 rows. Adding that together gives 23, so I need a microcontroller with at least 23 GPIO pins for switches. But if I want to drive any LEDs, for example, a caps lock LED, then I'll need an additional GPIO pin. So I'm going to look for a microcontroller with at least 24 GPIO pins. Next came the decision as to which microcontroller I should use. I was already familiar with the Arduino Pro microclones as I had used one of these for my macro keypad. Unfortunately, this didn't have enough GPIO pins. My next thought was the Raspberry Pi Pico, as these are low cost and have 26 GPIO pins exposed. However, 2 things put me off the Pi Pico. That was its size and the USB connector. I wanted my keyboard to have a USB-C connector, and the Pi Pico is fitted with a micro USB connector. Next on the list of possibilities was the RP2040 stamp. This utilizes the same RP2040 microcontroller as the Pi Pico, but with a smaller footprint and with more GPIO pins exposed, along with the USB pins being exposed. So I'd be free to use my own USB connector. This looks really neat, but retails at just over 3 times the cost of a Pi Pico. Then there was this, the PGA 2040. Like the previous 2 boards, this also boasts an RP2040 microcontroller, and is priced at just under twice the cost of a Pi Pico. I thoroughly like the look of this, and the space-saving method of placing components on the underside. One thing to note though is that by placing these components on the underside of the PCB, unlike the Pi Pico or the RP2040 stamp, it isn't possible to mount this PCB flush onto the main PCB without either a cutout or by raising it up on some pins. These pins and sockets are optional extras, which, if you go down that route, does increase the price and also the height. I ended up purchasing both the RP2040 stamp and the PGA 2040, and I had a play with both and ended up opting for the PGA 2040 because I liked the old school retro PGA look and feel. So then I set about creating the schematic for my keyboard, but I needed a suitable component and footprint for the PGA 2040, and I ended up creating these myself. To enable me to do this, I needed to know the pinout and pin spacing. Fortunately, this is on the Pimeroni website. Here, every pin is labelled, and look at the size. This thing is tiny. It measures just 20.3mm by 20.3mm. The pin spacing is a standard 2.54mm, centre to centre. So, armed with this information, I set about creating my own component in KiCAD. This is done from within the main project window in KiCAD and selecting the symbol editor. Within this area, you can draw out your symbol and save it. Let me open my version, so I'll search PGA 2040. And here it is. I simply drew a rectangle and added 48 pins, 0 through 47. I just left all pins set to passive since I didn't want to complicate things. And then I made sure that I labelled the pins accordingly. I then set about creating a footprint for the PGA 2040, and this is done in the not-so-mysteriously named Footprint Editor. Let's look at my footprint by searching PGA 2040. I started by drawing out a square measuring 20.3 by 20.3mm. I then added through-hole pads paying attention to the number and positions. Finally, using the Edge Cut tool, I drew a square in the centre of the footprint so that there would be a cutout. If you remember, this board has a lot of components on the rear, and by having a cutout, I'll be able to place the board flush to my PCB. So let's pop back into the schematic. Next, I needed to assign that footprint to the PGA 2040 component. This is done by selecting the component and pressing the E key on your keyboard.
And then browsing to the desired footprint.
Then it was time to start connecting things up. All of the ground pins are connected together and then to the ground. The VBus pin is taken to the global label VBus. The same for the data plus and data minus pins. The VBus, data plus and data minus pins are all going to be connected to a USB port. I've just connected them to a global label to keep the schematic tidy. You'll see in a bit where I have another global label with the same name that connects these to the USB port. Global labels sharing the same name are electrically connected without the need to draw a line between them, so using them really helps keep the schematic nice and tidy. The boot select pin is a special pin. If this is shorted to ground when the PGA 2040 boots, the PGA 2040 boots as a USB drive. This is how the firmware will be copied to the keyboard. So by connecting this pin to a switch, which is then connected to ground, it will allow for the possibility of updating the firmware in the future. When I initially drew this schematic, I didn't connect the GPIO pins to anything. This is because rather than connect them in order, such as row 0, row 1, row 2, etc., I wanted to connect them in a way that made for the easiest PCB layout. So at this early stage, until the location of the microcontroller is placed on the PCB, these can be left unconnected, and I'll show you how I decided how to connect them later on. I wanted to use an LED as a status indicator for the caps lock key, so I chose to use the next available GPIO pin. The LED itself isn't going to be on the main PCB, so I've connected the resistor and ground to a pin header. Then over here, the LED is shown connected to a socket. The LED and socket will be on the keyboard faceplate.
and the socket and pins will allow the two boards to be electrically connected together. Next was the USB-C connector. As this was my first time playing with USB-C, I wanted a quick and easy method of adding one to my design, so I opted for this Adafruit USB-C breakout board. Just like with the PGA 2040, I needed a component and footprint for the Adafruit breakout board, so I set about drawing one. Here is my symbol, and this was easier than the footprint to draw, as it simply was a rectangle with the pins named as per the Adafruit silkscreen on the breakout board itself. Like the PGA 2040 symbol, I left all the pins set to passive to keep things simple. Next, I created a footprint for the breakout board. I did this by measuring the physical board using a set of digital calipers and then drawing it in KiCAD. The plated through-hole pads use the standard spacing of 2.54mm center to center. On the top layer of my footprint, I added two surface mount pads so that I could solder the large fixing holes to my PCB. The only thing I'd change about this footprint were I to do it again would be the diameter of the through-hole pads. They weren't large enough for the pins that were supplied with the breakout board. Let's take a quick look in 3D at what this looks like. And finally, I added a link to the breakout board on the Adafruit website using the silkscreen layer, should someone else want to use this footprint and need more information on the component. I then connected my USB symbol to the VBus, Data Plus, and Data minus global labels that I mentioned earlier. So these are now electrically connected to the global labels over here. At this point, I still ignored the row and column labels as I didn't yet know what GPIO pins I'd be routing them to. I then created a second page on the schematic, which I can navigate to by clicking here. On this page, I drew out my matrix design as per my initial drawing, starting with column 0 and row 0 at the top left. Note that each switch requires its own diode. And if I zoom out a bit, you can see that the layout matches my initial drawing. Just heading back to the root page of the schematic, I want to point out at this stage of the design, I still had not connected the GPIO pins to any global labels, since which pin number I chose would depend on the PCB layout. So I then started to lay out the PCB, and this is started by clicking this button on the toolbar. This is my completed design, but since I'm working on a copy of the file, I'll go ahead and delete the entire thing and show you how I laid it out. And yes, I did double and triple check that I am working on the copy of the drawing and not the original. Clicking this button will update the PCB with all of the component footprints. Just before I click Import, let's take a look in the schematic where the footprints are assigned to each symbol. Selecting a component and pressing the E key on your keyboard will open the symbol properties. Here you can see I set the footprint of this switch to button_switch_keyboard SW_cherry_MX_1.00U_PCB. What a mouthful. And clicking here will show us what that looks like. And if we come down to the tab key, which is larger than a regular key, you can see here that this was set to a 1.5U key footprint. The caps key is larger still at 1.75U, and the shift key is 1.25U. And if we look over here at my enter key, you can see that I set this to the ISO enter key. All of these footprints are already built into KiCAD, so you don't need to worry about drawing them. The only thing you do need to ensure is that you assign the correct size footprint to each key. If you're unsure which key size to select for each footprint, go back to your layout at keyboardlayouteditor.com and select the key in question. And down here it will show you the width. So a standard key is 1 unit or 1U. If we look at the tab key, you will see that this is 1.5U and the caps key is 1.75. Right, you get the idea. Let's go back to the schematic. For each diode, I went with a surface mount footprint. This is the one I chose, the SOD-123. But there is nothing stopping you from selecting a through-hole version if you prefer. With that in mind, let's head back over to the PCB. We're going to want to add a grid origin somewhere up here. My file already has one, but so that you know how to add one, go to Place and then Grid Origin, and then click where you want it. This sets the coordinates at this point to 0, 0. So then I'll go back and update the PCB from the schematic. We're looking for no errors or warnings. That's good to go, so click Update PCB and close. I now have all of the footprints imported into the PCB design, and they are stuck to the cursor until I click and place them somewhere. You can just place these anywhere on the page. I then arranged the switch footprints. Now there's two ways you can do this, either the tedious manual way, or you can use the super cool plugin that I'll run you through, which will automatically arrange the switches and diodes for us. To install the plugin, go to the main KiCAD project window and select Plugin and Content Manager. And then search for Keyboard Footprints Placer, and then install it. Mine's already installed, hence I'm on the Installed tab. When it's installed, you'll get this icon up here. Clicking the icon will unsurprisingly run the plugin, and the first thing you're going to need to do is select a keyboard layout file. This is downloaded from your layout on keyboardlayouteditor.com. Remember I said you could save the design using your GitHub account. Now you'll see the benefit, right? So, click Download and select Download JSON, and note where you save it to. The JSON file contains the positions of each key and what size they are. Back in KiCAD, you can now browse to the JSON file that was just downloaded. Leave the standard size of 19.05 for both X and Y, as it is the size of a 1U key, with a little bit of a gap all around it. The plugin will assume the switch footprints are annotated with SW and then a number. If your switches are annotated with any other letters, then you'll need to amend this to match your naming convention. And the plugin also assumes that the diodes are annotated with D, followed by a number. Again, if this isn't the case for you, amend accordingly. An important thing to point out is that the plugin assumes SW1 and D1 belong together, and that SW2 and D2 belong together, and so on. Leaving Allow Auto Placements for the diodes will do exactly what it says. And Route with Switches will allow the plugin to auto-route the traces for both the switches and the diodes. However, I unchecked this as I ended up moving the diode slightly from the auto-placed position. There is an offset that you can play with if you want to automatically place the diodes with a specific offset, but I just manually moved mine. I didn't use the auto-generated outline for my design, but for this video I'll leave it selected so you can see what you get. And here I'll leave the delta to 10, so the edge of the PCB isn't hard up against the switches. This way there'll be room to add mounting holes. Then clicking OK will allow the plugin to work its magic, albeit with an odd shape at the bottom because the microcontroller and USB port need moving. I'll get rid of this bottom part of the PCB edge and move the microcontroller and associated components. We now have a basic layout of a keyboard. Let's take a quick look at the 3D render. You can see the switch footprints on the front and the traces, although for some reason it didn't route the function keys, and if I spin this around, you'll see the surface mount pads for the diodes. Next, you'll need to position the diodes where you want them and tidy up any of the routing. I'll start by connecting the column part of the traces. Notice how I'm using the top copper layer to take the traces vertically. It does help with routing if you can keep most of the vertical traces on one side of the board and most of the horizontal traces on the other. I'm actually going to get rid of this auto-generated PCB edge and make my own later on like I did for my original design. On my design, I moved all of the diodes down and over slightly so that I could connect them horizontally with a single trace. And then connect them to the relevant switch. On my design, I wanted the USB connector at the top left of the keyboard. Somewhere about here will do. I then placed the microcontroller fairly close to the USB connector. The boot select button that I chose has a button on its side, so I placed this right up against the edge of the PCB. My design features the caps lock LED on the keyboard plate. And I used jumpers to link the two PCBs together. Looking at my final design, you can see that I placed the resistor and jumper on the top right of the main PCB, and then on the plate PCB, I placed the corresponding jumper and LED. So for the design I'm running through in this video, I won't worry about placing J3 and the LED just yet. If you aren't going to use a plate to stabilize your switches, then you can do away with these jumpers and just place the LED directly on the main PCB. To do this, you'll need to ensure that you don't use the jumpers in your schematic. Before I position the jumpers and resistor, while I remember, I'll rotate the switch footprint around so that the button will be facing the edge of the board. To rotate, select the footprint and then press the R key on your keyboard. This will need to be on the edge of the board too, and it's at this point that we decide whereabouts the edge of the board should be. To define the PCB edge, select the rectangle tool, and then select the layer Edge Cuts. Next, draw a rectangle around the footprints. When you come to draw yours, you'll want to measure this properly and make sure that there is an equal space on each side and the bottom of the PCB. The distance between the top edge and the keys will be greater, as we'll need to encompass the other components. For this video, I'm just going to do this quite crudely, but for my actual design, I did take some time to work out exactly what measurements I wanted so that there would be an equal space all around the keyboard. Next, align the USB and switch footprints to the edge of the PCB. If you are using jumpers like me, simply move this jumper and LED out of the way for now. This jumper and resistor can, in theory, be placed wherever you like on the design. However, on my design, I placed them over at the top right. Remember when looking at the keyboard matrix in the schematic, I said that I didn't choose the GPIO pins until I'd started to lay out the PCB? Well, it's at this point that you can choose which GPIO pins you want to use based on the easiest way to route a trace to it. This way you can avoid the need for traces to cross over each other. In this current design I'm working on, because my schematic already has the rows and columns of the matrix linked to the GPIO pins, I'm able to connect this trace to a GPIO pin. You won't be able to connect the trace yet until the GPIO pins are linked in the schematic. So let's delete these two traces and look at how to do that. Once you decide on which GPIO pin to use for your row and column, switch back to the schematic, which, when I delete this global label, will look like what you see. So we have some GPIO pins without global labels. Let me just save this and show you what we see in the PCB layout if you don't have any GPIO pins connected to anything. Within the PCB editor, I'll update the PCB from the schematic so that those two GPIO pins won't be connected to the columns. Now you can see on my layout that it isn't possible to connect these to anywhere anymore as they aren't connected in the schematic. This is what you'll see when you first start to lay the traces out, and it is only when you decide which GPIO pin to connect it to and then update the schematic accordingly, and then in turn update the PCB from the schematic, that you'll be able to connect them. So route your trace close to the most appropriate GPIO pin that avoids the need to cross any other traces, and then pop back into the schematic to link that column or row to your chosen GPIO pin using a global label. For the two traces that I've drawn so far, that is column 0 and column 1. Save the schematic, pop back into the PCB, and click the Update PCB from Schematic button. Before I click this, just look over here at the two GPIO pins. You can see that there is no rat's nest between them and the traces that I drew. But when I update the PCB, you can now see that these two traces connect via the rat's nest to the GPIO pins that I chose. And we are now able to connect those traces to the appropriate GPIO pins. You now just have to repeat that process for each column and each row until you've connected them all. I pretty much did this one pin at a time, going back and forth between the PCB and schematic. You may find that you need to change the GPIO pin that you've already used. It's not a problem, just delete the trace and run through the process again. While doing this, don't worry too much about neatness, as you can always tweak the traces later on. Just concentrate on routing them to the microcontroller, trying to use the rule that most vertical running traces are on the top layer and most horizontal running traces are on the bottom layer, as this will help you out with your routing. When you do the USB-D plus and minus, theoretically you should route them using differential pairs, which means that KiCAD will automatically match the length of the traces. However, as this is such a short run, I'm just going to route each one individually with no regard to the length matching, as the difference in length will be negligible. Let's speed up the rest of the routing. Apart from this LED and jumper, everything is now laid out and routed. Running the ERC will tell us if we have any errors. Obviously, I expect an error for the unconnected LED and jumper, but let's just check everything else. 5 errors. Right, for the sake of keeping this happy, I'm going to connect the LED to J3 and then rerun the ERC. Now, just 3 errors, which all need fixing before we can move on. The description of the error tells us that there are unconnected items, the first being D48 and SW48, and here you can see I missed this connection. That's why it's super important to run the DRC before sending off your board for manufacture. Rerunning the DRC now shows no errors. So a quick look in 3D shows what we've got. And if all you wanted was a working keyboard PCB, in theory, you could stop here, albeit with an LED placed on this board instead. But before stopping, you may want to add some mounting holes, copper-filled zones, rounded corners on the PCB, and add some silkscreen to make it look a little more aesthetically pleasing. Next, if you want to add mounting holes, this is the time to add them. Press the A key to bring up the footprint selection and search hole. Choose the size of the hole you want and add it to the desired location on the PCB. You'll want to spend some time working out the exact measurements from the edge that you place the hole, and then replicate this around the edge of the PCB so that the mounting holes are placed uniformly. For this video, I'm only going to place this one hole and I'm not going to bother adding any more holes. As a personal preference, I think that PCBs with rounded corners look more aesthetically pleasing, and as such I used rounded corners on my design. To do this, place a grid origin at the top left of the PCB edge cut. Then select the Draw Arc button and Edge PCB layer and draw the arc of your desired size. Rotate if necessary and align it in the corner. This is a little trial and error until you get the rounding that you feel looks best. That was a radius of 2.5 mm. Let's see how that compares to a radius of 3.5 mm. Yes, I think the larger one looks better. So now this needs copying and pasting to each corner. Next, you'll delete the rectangle edge cut and draw straight lines on the edge cut layer between each rounded corner. Let's check that out in 3D. So you can see the lovely rounding corners and my one mounting hole. Do remember that you'll need to add more holes. I'm only using one as an example in the video. Assuming that you've routed all of the traces and it's past its DRC and that you've added all of the mounting holes, the next thing to do is add a copper fill zone that connects to ground. To do this, select Add a Filled Zone and then select Bottom Copper Layer. Then just click up here at the grid origin. It doesn't matter if I'm outside the edge cut here, as everything outside the edge cut will be ignored. Here you choose what net the filled zone should be connected to, so that's ground. Everything else can be left default, so just click OK. Then draw a large rectangle around the PCB, ensuring that you finish where the first line started. To see the filled copper zone, press the B key on your keyboard. And looking at the 3D render, if I spin this around, you can see the copper filled zone, and this is connected to ground. The copper filled zone isn't mandatory, but it's one of those things that I feel just makes the PCB look a little more professional. So let's do the same for the top layer. Now looking at 3D, you can see we've got a lovely copper filled zone on both sides of the board. Now the only other thing that you might like to add before sending the board design for manufacture is some silkscreen. I'll just open up my design here and you can see the mounting holes equally spaced around the edge of the board. And over here I've added some silkscreen text. Let's look at the 3D render and spin the board around. This text is to show my website, what the PCB is, its revision, and when it was made. And at the top, I added some silkscreen to aid in the assembly process. So here you can see instructions, solder pins on this side. Next to draw is the plate. For this, you'll copy the raw data from your design on keyboardlayouteditor.com. So that's all of the code on the raw data tab. And then head on over to builder.swillkb.com and then paste the raw data into this field. Next, you need to select what type of switch you're using. I'm using a standard Cherry MX, so I selected this one. The switch type denotes the shape of the hole that will be cut in the plate. Then for the stabilizer type, select the type of stabilizers you want to use. Again, I'm using Cherry. And this one allows for PCB mounted or plate mounted stabilizers. Everything else can be left default, and then that's it. Simply scroll down and click Draw My CAD. This free site is fantastic. How much time did that just save? To import into KiCAD, you'll need to download the DXF file. While I had my faceplate cut out of a piece of PCB, there's nothing stopping you from 3D printing this. Then you're going to need to pop back into KiCAD and import the DXF file that you just downloaded. So that's File, Import, Graphics, then browse to the download location and select the DFX file. Change the layer to edge cut. This means that when you import the image, all of the lines will become an edge cut on your PCB. Then click OK. And then you have your plate cutouts. I'll just hold them over the main PCB and zoom in a bit so that you can see that they are the correct layout and size. And you'll be using these on another PCB, so they can be placed out of the way down here. You'll need an identical PCB in terms of size and mounting holes for the plate. The easiest way to do this is to copy and paste the main PCB and then delete any footprints and traces that you don't need. Don't worry about the rat's nest linking the two boards. This will vanish when we delete the unneeded footprints. Before deleting any of the footprints, it's essential that the plate cutouts are aligned with the switch footprints or the two PCBs won't fit together correctly. The easiest way to do this is to select the plate and then move it over the copied main PCB. Zoom in nice and tight to be sure that the cutouts align exactly with the switch footprints. Spend some time doing this as the alignment is crucial. Before you delete any of the unneeded footprints, to avoid accidentally deleting any of the edge cuts, hide the edge cuts layer. Now select and delete everything else with the exception of the mounting holes and temporarily the jumper, since we'll need this to align J3. Obviously, on the version of the board I'm drawing for the video, there is only one mounting hole, but you will have more. Remember the LED and J3 that we temporarily left over here? Well, now you can grab them, bring them down over to where you are working. Double check which way round J3 should be orientated. Keep in mind that you'll be adding it on the rear of the PCB. To change J3 to the rear of the board, select it and press the E key on your keyboard. Then at the side drop-down, select back. This means that when you come to solder J3, the solder joint will actually be on the top of this board. Now J3 can be aligned with J2. Spend some time to ensure this is exact. Then select J2 and delete it. Then you can connect the LED and J3 with a couple of traces. When you've deleted everything, make the edge cuts layer visible again. Let's take a look in 3D. I forgot to delete the original edges in the DFX file. You'll need to ungroup the plate before you can delete these. I recommend grouping everything together afterwards so you don't accidentally move something out of alignment. Now, when I check the 3D render, it looks much better. The bottom of the board of my design was the easiest one of all. There are no component footprints, only mounting holes, silk screen, and copper fill zones. Again, the easiest way of getting this board outline is to copy and paste one of the above boards. Once pasted, ungroup everything in it and delete everything with the exception of the outer edge cuts and the mounting holes. And there you have the 3 boards. Now it's just a question of making them look how you want in terms of silkscreen and copper fill zones. On my design, I had copper fill zones on both the plate and bottom PCB. In terms of silkscreen, you can import images from the main KiCAD project window. Click Image Converter, then the Load Source Image button, and browse to your desired image. Finally, click the Open button. So here I have imported my channel name, and the image size is approximately 100 by 71 mm. Modify the size accordingly to what you want it to appear on your board. This can be a little trial and error, so again, don't be too concerned if it isn't right first time. Ensure that the PCB layer for the graphics drop-down is set to the side of the board that you want the silkscreen to appear on. And ensure that the output format is set to footprint. Then click Export to Clipboard. Then go back into the PCB editor and paste your image where you want it. With the pasted image still selected, press the E key on your keyboard to bring up the properties and deselect the Show checkbox on the reference line. Then a quick look in 3D. Looking nice. Before I placed any of the text above the caps lock LED, I checked what text was already going to be printed on the silkscreen layer. I chose to leave D89 to assist with assembly. If you do want to hide it, Select the component, press E on your keyboard and then change the layer from silkscreen to something like user. To add some text, I used the text tool, selected the front silkscreen layer and added an uppercase letter A above the caps lock LED to indicate what the LED is for. But of course you can add any text that you want. And checking in 3D shows the text. You can also use the silkscreen for notes to help with assembly, such as adding notes to say which side components should be soldered from. It's also a good idea to add silkscreen text that gives some information on what the PCB is, its revision, and the date. Line drawings like this lend themselves particularly well to silkscreen, and I place this on the rear of the bottom PCB. Before you send the Gerber files in for manufacture, it's essential to run a DRC, which stands for Design Rules Checker. Here you can see I have 8 warnings. Let's correct those now. This one is saying that the copper fill is isolated and not connected to ground. Well, on the plate PCB that doesn't matter. So let's just edit the copper fill zone and change that net to no net. Rerunning the DRC shows that I fixed those issues, but I still have 5 warnings. This reference is being intersected by the edge cut of the board. Well, I don't want that reference printed on the silkscreen layer anyway, so that's a quick fix. Edit it and either deselect the visible checkbox or change the layer. Rerunning the DRC shows that I fixed that issue, but I still have 4 warnings. We have the same issue on the other 2 boards with the reference being clipped by the edge cut, so again a quick and easy fix. Now just 2 warnings, both silkscreen overlaps. Again, similar issues with the reference being visible on the silkscreen layer and intersecting with some of the silkscreen. So let's hide those references. And running the DRC again shows no more warnings. Fantastic. Before exporting the Gerber files for manufacture, I usually like to save and close my design, and then wait a day or so and review them again with a fresh set of eyes, as it is so easy to overlook something. Next, assuming that you are happy with your design, before you export them as Gerber files for manufacture, you'll need to split this single design into 3 separate PCB files, one file for each PCB. The easiest way to do this is to save a copy of the file. So the first one I'll name Bottom Mechboard, and the next one Middle Mechboard, and finally Top Mechboard. Now, when I look in the main KiCAD project window, I can see the new PCB files I've just created, top, middle and bottom. You'll then need to open each of these new files one at a time and remove 2 of the PCBs. So this is the bottom file, so we don't need the middle or top board. So delete these and save the file. Next, you'll need to do the same for the middle and top PCB files. Right, now you're ready to get these manufactured, so you'll need to export them as Gerber files. PCBWay have an excellent plugin that will automatically do this for you and even upload the Gerber file to their site for easy ordering. You then just need to select the required quantity and color. For my design, I went with a white PCB and black silkscreen, and I had a lead-free surface finish. Then, just repeat that process for the other 2 boards. Installing the PCBWay plugin is super simple. From the main KiCAD project window, go to Plugin and Content Manager. And on the Repository tab, search for PCBWay plugin for KiCAD, and then install it. I thoroughly recommend the PCBWay plugin, as it makes exporting the Gerber and ordering so much easier. On my design, I also had some color images printed. PCBWay now offer color UV printing direct to the PCBs in addition to the regular silkscreen. This means that you can have color images printed directly on the PCB. The color image that you want printed needs to be saved inside the Gerber zip file, along with a PDF or vector image showing the placement. To further help with placement of the image, you can add notes on the fabrication layer of your PCB. This is the faceplate that I had manufactured, and I added these notes here saying I wanted the cassette image printed here as per the example file that I had placed in the Gerber file. This was the file that I provided showing where I wanted the images placing on the PCB, and also indicated the file name of those images. I provided each image as both a high-resolution PNG file and as a vector image. Let's take a look at where in the Gerber file you place these additional color images. The quickest way to obtain the Gerber file is, after using the PCBWay plugin, simply download it from their site. The Gerber file is a zip file that contains all of the necessary information for your PCB to be manufactured. I created a folder called color_UV_print_readme, and inside this I placed my images and reference file. I then placed that folder inside the Gerber zip file and used this modified Gerber zip file to order my PCB.
Join me next time for part 2, where I'll be covering the build, firmware, and of course, using the keyboard. Subscribe and hit that bell so that you will be notified when part 2 is released. Click here to watch what YouTube thinks you will enjoy the most, and click here to watch part 2 when it is released. Until next time, take care.